I'm Roger Diaz, and on behalf of our research team, I'm going to present our study, which is funded by Trish. So let's start with the background, right? The rationale for which we are conducting this research study. As everyone knows, in-flight medical events pose significant risk to crew safety, health, and the mission success. Also, when we think about deep space and long-duration missions, the space crews will have to be prepared for progressively Earth-independent medical care capabilities. And within a certain spectrum, these space crews will have to be able to provide medical care in a fully autonomous way. So the study aim here was to design, develop, and test the feasibility of an extended reality platform for in-flight medical training. And the context here is that for deep space and long-duration missions, we will need to provide in-flight training, refresher training for astronauts to be able to manage medical emergencies with competency. So in this study, we created this extended reality platform to deliver extended reality medical scenarios in 3 different modalities. So the first one you can see here is fully immersive virtual reality through a headset, through a head-mounted device. The second one is the delivery of virtual reality through a desktop, a screen-based, desktop-based virtual reality. And the third one is augmented reality. So it's the delivery of a XR scenario via a mobile AR modality, in this case here a tablet. So we're gonna show how we develop these XR scenarios and how we deliver these scenarios in these 3 different modalities. So as methods, we're going to divide our methods here in the scenario creation, the space health scenario design, development, and creation, and also the extended reality platform development, how we developed the application to deliver those scenarios. So let's start here with the scenario design, right? So we used a backward instructional design to design these medical scenarios, simulated scenarios, starting with the learning objectives and then going back to the different factors and components of a scenario. So we start with what are the learning objectives for determined medical condition, and then from the learning objectives we can design and develop the components of the curriculum. We design and develop 2 different medical scenarios, one including a tension pneumothorax and the second one involving a smoke inhalation. We use branching narrative with a foldback structure that I'm going to show in a few minutes to create a interactive scenario in which the participant, the learner, can not only watch and observe what's happening, but can actually be part of the story and make decisions. And based on those decisions, we have different branches based on specific medical conditions and the decisions that the astronauts would make during those medical situations. So we developed this interactive storytelling that are prompted by users' medical decision making to allow the user not only to watch and observe passively to these medical scenarios, but actually to be part and decide on what are the actions of those astronauts taking care of a medical emergency in space. So if you take a look here, this is our general design of one of the scenarios. This is the pneumothorax scenario, in which we have here a start point, and then we start designing all the branches. You can see here the branches for medical history, and in the bottom the branches for physical examination. And you see that for each of these branches we have some shots here, shot 1, 2, 3, and this is to inform the video production, the scenario production later. And also in all this design, the educational design matches what's needed for the production phase, but also matches what's needed for the software architecture. So we have here some system prompts and some information that will be used as a wireframe for the software developers later to design and program in the Unreal Engine what it's going to be this extended reality scenario. When you think about the development per se, we use three different components here, right? The first one is the three-dimensional photogrammetry of a spacecraft simulator. So at Stratus Center for Medical Simulation here in Boston, we have a spacecraft simulator that was built from another grant a few years ago. And our goal here was to virtualize that environment, to take that environment, that's a physical environment simulator, and virtualize that into like a virtual reality environment using 3D photogrammetry in a way that we can capture exactly what is there in the physical space with the same dimensions and put that in the virtual environment. Then what we did, we had the environment, we needed the scenarios, right? So we use this technique called volumetric video capture that can capture professional actors in 3 dimensions. So it's a video in 3 dimensions. And then third here, I'm going to show a little about our back-end and front-end development using the Unreal Gaming Engine. I would like here also to acknowledge the role of our partners, industry partners, who helped us to develop these medical scenarios and platform. So let's take a look inside each one of these three components here of development. The first one is going to be the 3D photogrammetry of the spacecraft. So this is the Stratus spacecraft simulator. This is the physical simulator here. And our goal, as I mentioned, our task was to virtualize this. So our team came with these techniques and a series of devices. This is a LiDAR device that can actually scan the environment and capture all the dimensions and the texture of this environment, and then we can later virtualize that. So here is the day that we were capturing the physical environment in 3 dimensions, and then this is the result, right? This is the virtual asset created from that photogrammetry, and you see that with this virtual asset, it's the actual environment here virtualized, right? And you can not only look around like a 360 video, but since this is a 3 dimension, you can see that we can walk around the space, and the space has, as I mentioned before, exactly the same dimensions as the physical one, right? So it's exactly a replica, a virtual replica of the physical environment. This way, we want to create here what we call environmental fidelity of these medical scenarios, that the environment is exactly the same as we have in this simulator. So let's take a look now at the volumetric video, right? We have the environment, now we need the scenes, we need the people inside this environment during a medical emergency. So as I mentioned, we had all that design, the branches, informing not only the software architecture, but also informing the video production. And we use a really professional video production team in Los Angeles. Here is our team, our director, and we have screenwriters, like a movie production, to really produce a high quality scenario. And here we have the actors during rehearsal, and you can see here in this stage, this is a 3D volumetric capture stage that has more than 100 cameras capturing the actors and the scenes from all possible angles, and then creating this 3-dimension asset. Here they are rehearsing like one of the procedures during intentional pneumothorax. Here our entire team, so we have a multidisciplinary team of physicians, educators, video producers, and XR experts to create this experience, really to produce this experience in a multidisciplinary manner. So here is the final result of the 3D volumetric capture, right? So you can see that
Hey, Brett, I'm going to hook you up to the heart
captured in
monitor.
Los Angeles, and our environment was captured in Boston. So you can see here the realism of these 3D assets, and you see that it's not a 360 view, it's actually a 3-dimension asset. You see that you can walk around.
Okay, give me your finger. I'm going to
those
check your
assets,
oxygen saturation.
and they are with the same dimensions, the real ones, and allow us to have this 6 degree of freedom.
Okay, let me have your arm.
experience. Now, we have the environment captured via photogrammetry in Boston. We have the actors playing a medical scenario and captured in 3D volumetric in Los Angeles. Now, our development team put them together, right? The video volumetric assets inside the virtual simulator, the virtual spacecraft. And that's what I'm going to show later in the results section. But before that, just would like to show a little here about our development process. So I mentioned we use the Unreal Engine, and this is the blueprint. This is what looks like inside the software, right? With all the branches, all the different functions to play audio, video, and all the interactive capabilities. So you see how complex it is, a 8-minute scenario. This is the pneumatoric scenario, it's an 8-minute scenario. How complex it is, the development phase, in which we have to create all these branches and all this logic to make sure the scenario can respond to the decisions of the user, the learner. Now let's take a look on the results, right, and what we were able to create using this method. So as I mentioned, desktop-based VR here, 3 modalities, right, fully immersive virtual reality using a head-mounted device, and then mobile AR, augmented reality, using a tablet. Let's start with the desktop-based VR. I'm going to show you here one of the usability testing experiments that we did. So you see the user using a headset that is a EEG device that measures his brain activity. Here the software can capture all the brain activity, heart rate variability, galvanic response, a lot of digital biomarkers. Here is the eye tracking. We're also using eye tracking glasses, and we can see where the attention is focused on. So all these digital biomarkers are being collected while the user is interacting with the virtual reality scenario. Then we have a lot of automated objective metrics of engagement, presence, cognitive load, and stress. And we can compare the different modalities with all these objective metrics. Here's the Empatica device. This is a smartwatch measuring skin galvanic response, heart rate, and also motion. So all this data were collected in all the modalities. So I'm going to show now the next modality, that's the fully immersive VR. So the user is wearing a headset. And now you see that they are fully immersed. So they can see the patient monitor there, they can interact with the scenario, they can walk.
Okay, Parker, I brought the medical checklist up on the tablet. You'll see it on your screen.
They can interact with the medical checklist, make decisions. And you see that's a much more immersive experience because they are with the headset, so if they look around, they only see they are really inside the virtual environment. Now let's take a look on the mobile AR, right? So we have the physical environment overlaid with virtual assets.
I have the medical checklist up on the tablet. Which one should we choose?
Eye tracking glass, but can actually see an overlay of the virtual assets on the real physical one, right? And an interesting thing here in this one is that if you take a look here, so they have the real environment, we have digital astronauts, right, were captured before. And here we have Maddie Abnelli, who is our postdoc. It's a real person here. And you see that the realism of the digital avatars, it actually looks like the digital avatars are more real than the real person. So as conclusion here, right, the main purpose here is to prove feasibility. That's feasible to create this highly realistic and engaging medical scenarios using XR technology. Second one is that this is an ongoing research, and as I mentioned, we are still collecting usability data using human factors and cognitive engineering methods as a way to get user feedback and using like a human-centered approach to improve the experience, improve the interaction with the XR environment experience, and also improve the learning experience. And lastly, we are also running some ongoing experiments to investigate the difference between the different XR modalities, right? Desktop-based, AR, and fully immersive VR, as it relates to cognitive load, engagement, presence, and learning outcomes. Our hypothesis here is really related to that a fully immersive environment will be more engaging and will promote better learning outcomes compared, for example, with a desktop-based device or environment. However, since this is a really emergent field, right, that those findings will be very helpful because, of course, the type of device, the technology you need to deliver an experience like this one in a PC, in a cell phone, or like in a fully immersive headset is different, right? The cost of this device is different. So we really hope that the findings of this study can help us to better understand and also to select the best devices to deliver this type of extended reality medical scenarios, and maybe find out that there is no difference between them, and you can use, for example, simple laptops to interact with the scenarios with the same level of engagement, the same level of learning outcomes. So those will be like the final results of this research that I look forward to presenting in the IWS 2023. So thank you very much again for your attention and for the opportunity to present our research here.